السلام عليكم.
السلام ورحمة الله.
Everything is fine inshallah.
نعم دكتور.
I am turning off my video, Ibrahim. Okay, wait only 1 minute, then we'll start. Then we will have. Who's going to go first?
I'll go first, doctor.
Okay, so you first. Who is second?
Tarifa and then Muhammad.
Muhammad. Great. Just a couple of. Yes, come in. Okay, Ibrahim, whenever you are ready, you can start. Share the screen to everyone.
Inshallah. Can you see my screen?
Yes, I do. Yes. Yes.
Right. Okay, so hello everyone. My name is Ibrahim Al-Sabt. I'm a research assistant in the CubeSat laboratory. Today I'll be presenting SharjaSat 1. I'll give an overview on how will it contribute to life.
The audio is weak, Ibrahim. The audio is weak. Can you check why?
What about now, doctor? Better?
No.
Is it better now, doctor?
Yes, it is.
Okay. All right. So as I said, I'll give an overview about SharjaSat 1 and how will it contribute to life improvement. So starting with SAST, I'll give a brief overview about SAST. So SAST is the Sharjah Academy for Astronomy, Space Science and Technology. It was established on May 2015 to implement the vision of His Highness Sheikh Dr. Sultan bin Muhammad Al Qasmi in establishing a center that involves science and technology at a national and international level and contribute to the research and development in the space sector. So mainly the SAST consists of research laboratories, observatory, planetarium, and space exposition, and the academic affairs and the administrational affairs. So the main activity of research and contribution to research is in the 5 main laboratories at SAST. So the labs are the CubeSat lab, the radio astronomy lab, the meteorite center, the high energy astrophysics, and space weather and ionosphere lab. So as a vision of the CubeSat laboratory and at SAST, we have a mission of designing and development of CubeSat technologies and their subsystem from scratch until launch. Also, we design and develop a CubeSat to provide economical access to space, as well as SAST CubeSat program for development and operation of nanosatellite that add exciting challenge to student experience as long as we involve students in our projects. However, we also aim to build capacities and expertise in CubeSat technology and innovation. And finally, we contribute to the research and development in satellite and related technology to support the growth of the UAE space sector. And as a vision, we have a vision of that we are aiming to lead in the research and development of the CubeSat technology while providing services to educational institutions to accelerate the UAE's space sector. So as you can see, in the CubeSat lab, we have three main units. For me, I believe the CubeSat lab should be called a CubeSat infrastructure because we developed the CubeSat from the very beginning, from the scratch until launch, as I said previously. So we have three main essential units for CubeSat missions, starting with the high performance workstations that we use to design and simulate the CubeSat mission in general. And then we use our clean room, which is certified ISO 6 clean room, to integrate the engineering and the flight model of SharjaSat or any CubeSat in the future, and as well as we are going to test those CubeSats in those clean rooms, in this clean room. So as you can see here, where I appear in the picture with Engineer Bogash, we are performing a functionality test for SharjaSat 1. Also, we have the ground station. I won't go in details for the ground station, but we use it for tracking and receiving telemetry and data from the CubeSat. My colleague, Engineer Tarifa, is going to explain and give an overview about the ground station in the next presentation, actually. So now that we know that CubeSats are, we know what we have as a facility in the Sharjah Academy, let us define what are CubeSats. So CubeSats are nothing but many version of larger satellites. They they host and contain the same subsystems, same systems that are included in larger satellites. But as a CubeSat engineer, we are restricted with many specifications. So for example, we have to stick, if we are building a one unit CubeSat, we have to stick to some dimensions such as 10 by 10 by 10 centimeters for each single unit. Also, we have to stick to the mass of the CubeSat, where it should be 1.33 kilograms for the one unit. But however, if we are looking forward to increase the size of the CubeSat, then we can go on the multiple of one unit. So we can have a 2-unit CubeSat, which can be by the dimensions of 10 by 10 by 20 centimeters as a height, and we can double the mass as well. So usually CubeSats are deployed into lower Earth orbit, which we call LEO, for many purposes, for communication or scientific experiments. I'll talk further about this in the next slide. So in general, the CubeSat systems are divided into two types. So we have the payload, which is the main system that will achieve and is responsible of achieving the satellite mission. And we have the bus system, which supports the payload to achieve its mission. So for example, an example of payload, we have Earth observation payload, simple cameras to perform some Earth observation, as well as communication to test communication. So mainly the communication is used by radio amateurs. Also, we can prove technologies. We can develop a total new payload to prove a technology or prove a concept by using this technology in space, as well as studying some space phenomena. In terms of the bus system, as I said, the bus system are there to support the payload in achieving its mission. So for example, we have the onboard computer, which is the central mind of the satellite, if we can call it a mind of the satellite. So it gives commands to other systems. It give commands to the payload and other subsystems. Also, we have the attitude determination and control system, which is mainly a system that is responsible of the attitude and the orientation of the CubeSat while it's in orbit. The communication system is used to communicate with the ground station. The power system consists of the solar panels, consists also of the batteries and the EPS board, which is mainly responsible of distributing the power, the sufficient power to other subsystems. Also, we have the structural system, which is the system that hosts all other systems in the satellite. So, speaking of ChargeSat-1 now, and I'll start giving the overview about ChargeSat-1 mainly. Here we have the mission patch, which illustrates the mission of ChargeSat-1. We can see the CubeSat, which mainly consists of 3 units. We can see the sun at the background. We can see the Earth as well, because our mission involves the sun and involves Earth as well. So ChargeSat-1 is the first CubeSat mission to be developed by SAST engineers and students as well, because we involve students to prepare them for future challenges in the space sector. ChargeSat-1 main payload is an improved X-ray detector, and its objective is to investigate the hard X-ray emission from the sun and other bright X-ray sources in the universe. So speaking of ChargeSat-1 objectives, ChargeSat-1 is a 3U plus CubeSat mission. Why am I saying 3U plus? Because as we can see here, there is a part that is going out of the CubeSat. This is the plus unit that I'm speaking of. So we call it a 3U plus. However, the main objective of ChargeSat-1 is to observe and study the solar coronal holes and their effect on space weather, as well as to detect the hard X-ray from very bright galactic X-ray sources, such as black holes and neutron stars. So, as an overview of ChargeSat-1 and what it will be hosting within its structure. So mainly the payload is, as I said, it's an improved X-ray detector. Why we are calling it an improved X-ray detector? Because this technology have been used before once at the Beagle satellite, but it was not successful. So we are improving it now in order to make it a successful mission to achieve the scientific goals behind this mission. So beside the payload, we have the subsystems of ChargeSat-1 that support the system, the payload system, which is the onboard computer. And as I said, it is the main or the central mind of the satellite, which makes which gives the command to other subsystems, which give the commands to all systems in the satellite. The attitude determination and control system, as we can see in the figure on the right, the ADCS consists of many units, starting with the reaction wheels, star tracker, magnetic torquers, LDRs, sun sensors, nadar sensors, primary redundant magnometers. The ADCS computer has its own onboard computer to give its own command, as well as the control software. In terms of the communication system, it varies between different mission of CubeSats. So in the communication system in ChargeSat-1, it is going to communicate through S-band frequencies as well as UHF and VHFs. The power system, as I said previously, it consists of the solar panels, the batteries, and the EPS system in order to support all subsystems with the sufficient power. The structural system is the structure of the CubeSat, the skeleton of the CubeSat to host all subsystems within it and to ensure the success of the mission. Also, we have the thermal system. The thermal system is a passive control on ChargeSat-1. It will consist of battery heaters, Captain Myler tapes, and solar panel covers. All right, so if we are wondering how will ChargeSat-1 contribute to life improvement, we have a phenomena of satellites failing while they are in orbit due to the space weather conditions. So SharjSat-1 will focus on detecting the X-ray emission from the sun and conduct exclusive study about sun corona and its effect on the space weather conditions during the solar activity period. So such studies will help in demonstrating the relation between these phenomena, and as a result, this study will help in the prevention of these failures in space missions. As well as SharjSat-1 is contributing through capacity building as it involves students in order to ensure that the future generation will have the required skills, the required knowledge in order to contribute for further space exploration and face these challenges in the space sector. With this slide, I conclude my presentation today, and if you have any questions, I'll be more than glad to answer. Thank you.
Thank you very much, Ibrahim, for this very informative lecture. So please, if you have any questions, any comment for Ibrahim, so please move forward, please. I would like to chat or send a question by chatting, so please. Okay, everyone is shy. So, okay, let us ask Tarifa to share the screen and to start her presentation. Tarifa.
Yes, I'm sharing my screen now. Can you see my screen?
Yes, go ahead, Tarifa.
Okay, good afternoon, everyone. My name is Tarifa Al-Kaabi, a research assistant in the CubeSat laboratory at SAST. And my presentation today will be about tracking satellites with ground stations. So I'll go through a quick introduction to the ground segment of the space mission, and then some concepts and terminology related to tracking satellites. We'll have a look at our own ground station at SAST and how to use it to track a satellite, and I'll conclude with some remarks. So firstly, any space mission consists of three main segments: the launch segment, the space segment, and the ground segment. The launch could mean the launcher, the launch site, and so on. The space segment is the main spacecraft with its payload and spacecraft bus. And the ground segment, which we are concerned about in this presentation, it consists of all the ground-based elements of the mission. It enables for the management of the spacecraft and the distribution of its data, whether be it the payload data or the telemetry among the interested users. It could mean the ground stations, the mission control centers, or even ground control networks. But ground stations in particular are the parts that provide the radio interferences between the space and the ground segment for the telemetry tracking and command, or the payload data transmission and reception. So through ground stations, we can uplink or send signals, or we can downlink or receive signals from the satellite. So you need to know some terminology and concepts if you want to track a satellite. For example, the passes and the footprints. A pass is when a satellite flies overhead. There's a line of sight between it and our ground station, and this pass depends on the location of the ground station and the characteristics of the orbit of the satellite. While the footprint is the ground area where the satellite offers communication to the ground stations in this area. So for example, you see here, this footprint is for this satellite, so any ground station in this area could communicate with it, but if you are outside of this area, you can't reach the satellite. Another thing is azimuth and elevation angles. And these are measures to identify the position of the satellite flying overhead. For example, the azimuth varies between 0 to 360 degrees. So when you are at north, you are at 0 azimuth, and you move clockwise So it is 90 degrees east, 180 degrees south, and so on, where the elevation varies from 0 to 180 degrees and shows where the satellite is above you. So when a satellite first rises from the horizon, it is at 0 degree elevation, and then when it's right above you, it's at 90 degree or at the zenith, and while it's setting, it is at 180 degrees. So you need to know these angles at the azimuth and the elevation in order to point your antennas accurately to the satellite and get the best signal possible from it. So the communication of the satellite employs the electromagnetic waves for transmission of the information. And usually higher frequencies are employed. And this is because lower frequencies can be reflected by the ionosphere. So usually we need, our satellites use the frequencies above 100 megahertz. We can see them usually in the VHF, UHF, and SHF, which are the very high frequency, ultra high frequency, and the super high frequency. And the super high frequency includes the L band, S band, C band, and so on. And there are physical, technical, and legal limitations to dictate allowable spacecraft communication frequencies. And these are regulated by the ITU, or the International Telecommunication Union. So communication involves the translation of information in a form that we can move from point A to point B. And there are basic components, and they are the same in the ground station and on the antenna. So you need a transmitter, receiver, modulator, demodulator, and the antenna. For example, on the spacecraft, the bus and payload information is modulated, which means they are combined with a carrier signal to be transmitted through the antenna to the ground station. And similarly, when we are sending commands from the ground station, these commands are received by the antennas, demodulated to extract the commands from it. Modulation basically means combining the message or the information signal with a carrier signal, because usually the information is at a lower frequency. So it, as I said before, we need to transmit signals in a higher frequency to overcome the effect of the ionosphere. So you combine it with a higher frequency carrier signal, and this will transmit the signal more efficiently. And usually the modulation is in two basic types, the analog and the digital. And these happen by changing the amplitude, the frequency, and the phase of the signal. And you can go deeply into these, but the basic or the simplest type of the digital modulation is the Morse code, or the CW signal, which is also called the on-off keying signal. So coming now to the SOST ground station. Now that you know the importance of a ground station, we have installed the ground station for the purpose of monitoring our own SharjahSat-1 that Engineer Ibrahim has just talked about. And this was in February of 2020. This ground station also sets up the infrastructure for backing future satellite missions. So as he just explained, the SharjahSat-1 utilizes an S-band transmitter for the payload data and the UHF-VHF transceiver for telemetry and commands. So we need our ground stations to accommodate for these frequency bands. So you can see here the hardware that we have implemented, which is basically the VHF and UHF antennas. We have two of each. They are of the Yagi type. The rotator in the middle that gives the turning range of 180 degrees in elevation and 360 degrees in azimuth. We have the cabling and the mechanical construction that holds everything. And inside of our ground station cabinet, we have our radio transceiver, which is the ICOM IC9700. We had the elevation azimuth dual controller and the rotator control interface, and of course the computer. So together, along with our outdoor hardware, these provide full autonomous control of our system, and we can also control it from inside of our CubeSat laboratory. As for the software, we are using the Ham Radio Deluxe for tracking, for generally tracking satellites. and these include the 3 different modules: the rig control, the satellite tracking, and the rotator control. And we also have a custom-made software for the ChargerSat-1 mission. This will provide mission control attributes and the means to interact with the mission when it's in orbit, with 3 main functions, which is to issue telecommands, and these are available as buttons, as you can see here, to process and display telemetry, which include general telemetry of the satellite or subsystem specific, and lastly, to export the telemetry and photos to be saved on the hard drive. So let's have a look on how we can use a SAS ground station to track a satellite. So first you need to switch on the devices and to start the ham radio JRX, which will start automatically the 3 different modules. Then on the satellite tracking module, you need to, you can see all the satellites that you can track, and we can also make customized groups based on the type of satellite or the type of modulation used by the satellite. And so here we have 2 groups that we have made for CW, or the Morse code, and the AFSK modulation. And if you press on next passes, you can see the next passes of these satellites. You can check the name of the satellite and the time of the pass. And you can see here on the graphs the elevation angle. So usually if the elevation angle is above 20 or from 30 to 50, it's going to get us a good signal, because lower elevation angles would not give a good signal. So we need to pick a satellite, a pass from these. Then on the same satellite tracking module, you need to turn on the tuning dial and check the frequency. And you can check from an online source if it's the same frequency as published by the satellite developer, then you can leave it as it is, or if not, you can change it. And then you need to turn on the rotator on the satellite tracking module and also in the rotator controller module. So you just need to connect it and turn on these 2 buttons. Then you have to wait until your ground station enters the footprint of the satellite. For example, you can see here the footprint of the satellite moving as it moves in orbit. And as it is moving, we can see the rotator tries to follow it. These 2 videos are sped up. In reality, it's much slower than this. And once it is your ground station is in the footprint, you can start hearing the signal. It would sound something like this. So you can hear some clicking sound. These are the pulses from the rotator controller to the rotator to tell it to move. And you can see the beeping of the Morse code. And so this signal, you can connect your microphone to record it and then decode it. For example, this is a signal that we got from the Move to satellite, which is a satellite by an educational satellite by the German Aerospace Center, the DLR. This satellite transmits its call sign in the CW or the Morse code every 40 seconds, and a short beep every 10 seconds. And if you can hear here, so this is the signal that we got. And here we used an online Morse decoder to decode it. Okay, so here you can see the call sign. The call sign is basically a unique transmitter designation. So any transmitter should have its unique call sign. And so finally, you can put your rotator back in its park position where the elevation and the azimuth are at 0, and switch off all the devices. So you have seen how the ground station is an important aspect of a space mission used to support communication with the spacecraft. Our ground station is fully operational in the UHF, VHF amateur frequency ranges, as well as the CubeSat team at SAST is licensed to operate it by the TRA. And future work of our ground station would include the installation of the S-band dish antenna to support the download of the SharjahSat-1 payload data. Thank you for listening, and please feel free to ask any questions you have. Okay, since there are no questions, I'll pass it on to Engineer Mohammed.
Thank you. Can you hear me clearly?
Yes.
Okay. Can you see my screen now? Yes? Okay. So hi everyone. I am Mohammed bin Ashur, CubeSat from the CubeSat laboratory. My presentation will be a continuation of what Engineer Ibrahim and Engineer Tarifa said. It will be rather focused on the educational outcomes. So starting, this is the outline. I will give a brief overview on the CubeSat missions, their capabilities, some examples, and some numbers regarding the missions, and then focusing on the university class spacecrafts and their educational outcomes, the student workshops, and conclusion. So here we can see like a full spectrum of the satellite classifications. On the extreme left, we can see the Femto, Pico, Nano satellites. So they are mainly for, you can see the prices, they're affordable by universities. And on your extreme right, you can see the huge communication satellites that are mainly focused for big companies that they spend a lot of money. And in the middle, you can see so many observational satellites, scientific satellites, and in between. So our focus will be mainly about CubeSats here. So main points to remember from the previous presentations is that CubeSats are accessible to all students, researchers, and commercial entities. Nowadays, even students in elementary school, middle school, and high school had worked in CubeSat missions to launch them into space. Also, another thing to keep in mind is the size and weight. So you have a limited size. I didn't catch that. Could you try? Sorry. You have a limited size and weight. Also, another thing, if you have a low cost, so when you have a low cost, you can accept higher risk, which is very good. Another thing is the development time. You don't need to wait 5 to 10 years and work on this big satellite to launch it. Instead, you can work for maybe less than 2 years to launch your CubeSat. You can demonstrate technologies, new technologies. Of course, your objective should be focused since you have a limited space. And of course, other things to look at are the launch and the space debris issue. Moving into the applications of CubeSats, you have the Earth observations. Of course, since they are orbiting in the low Earth orbit, also can be used for communication, for different scientific objectives, such as SharjahSat, as Ibrahim said, or a technology demonstrator, or even an interplanetary mission. I'll give here 2 examples. The first one will be the Marco A and B. So before going beyond Earth, now when the CubeSat is orbiting Earth, you have several advantages, such as the communication. You can communicate easily since you have ground stations everywhere. As Tarifa said, we have a ground station here at Sharjah Academy to communicate with satellites. Another thing is the navigation. You can use the GPS to locate your satellite. You have also the magnetic field around the Earth, which acts as a shield, protecting from highly energetic particles. Also, the magnetic field can be used to orient the spacecraft and to add some sensors. For the power, you can use the sun. And for propulsion, you don't need a propulsion. So all these things I mentioned are not available for this CubeSat. As you see in the picture, there are the Marco A and Marco B. One of them is folded up, as you can see on the left, and on the right, you can see everything is deployed, including the solar arrays and the big antenna. This is a very impressive project and a big milestone since it's a new in its nature. For the communication, they used the big antenna. For the navigation, also it was very challenging. So they have to use the deep network, NASA deep network communication antennas, and including like the power. The power is limited. The propulsion, they had to use 50% of the CubeSat as a propellant. And as far as I remember, Marco B, I think, had a leak in one of the thrusters, so it was a problem, and the team managed to overcome that. These CubeSats are actually sent with InSight. InSight is a lander lander in Mars. Unfortunately, when InSight was planned to launch, there was a problem that the orbiters around Mars won't cover that position, so they won't give a real-time relay. So they had to come up with these two CubeSats to give the real-time relay. Moving on to the second example is remove debris. Actually, this is a microsatellite, I think around 100 kilograms maybe. It has will deploy two CubeSats, two U CubeSats, and it will be mainly to demonstrate the new technology. So they wanted to. They knew about the problem with the space debris. So there is a clever way, like different experiments they wanted to do to know which experiment works better to remove these debris from, at least from the low Earth orbit. So they used the VBN, or the visual based navigation camera. They launched this DebriSat-2 from the microsatellite, the spacecraft here. So they launched it, and then the camera has to look at this CubeSat and do some calculations to understand how to react and how to act if this was a real, like this CubeSat was acting as a debris. Another thing, they used the net capture, where they launched DebriSat-1, and then they launched the net to capture it as another experiment. The third one was a harpoon, where they had a fixed target on a panel, and then they launched this harpoon to penetrate this target. They wanted to know how does it act in these conditions, especially that you're not in the lab anymore, you're in real space, so how will it act? And finally, this satellite, will launch a large sail, which will increase the drag and bring the satellite back to burn from the atmosphere. They actually managed to take videos, so it's actually interesting. If we can see here, this is the net experiment. If you can see here, this is the CubeSat, and this is the net. So as you can see here, it captures the CubeSat successfully. Actually, the CubeSat here actually inflated a large target to increase like the area to make it easier for the net, and they just about caught the CubeSat. Here you see again, there's the play. Okay, it's the same thing. So let's move on to the harpoon experiment. If you can see here, this is the target, and they launched the harpoon into it. Just a second. This is another way. I think this is an aggressive way to deal with the space debris. Okay, moving on. So we saw some capabilities of these CubeSats. These CubeSats can do whatever you want as long as you are a clever engineer and you can come up with new solutions. And now launching these CubeSats to satellite, to space, sorry. First, on the left, you can see the traditional way. You can see the big payload, this big spacecraft. And then if you see the red circle here, this is the 3U deployer from the rocket. So you basically, you can't actually choose your exact orbit. Your orbit is actually decided by the primary player, because he'll pay for the whole mission and you pay like, or even you can get a free ride. On the right, you can see the CubeSats here. You can launch them from the International Space Station. Either you send them as a cargo with the food and other supplies for the astronauts, and then the astronauts take these CubeSats and then they can launch them from the Japanese module into space. And in the middle here, you can see the Indian rocket, ISRO, I believe this was in 2017. This rocket had 104 satellites and 103 of them were CubeSats. So this was a very big milestone for CubeSats. Now, okay, we talked about CubeSats. Let's see the exponential growth of CubeSats. On the left, we can see starting from 2000 or 1999, when they started these CubeSats missions. You can see from 2000 till 2012, approximately, we launched 100 CubeSats. We just exceeded 100 CubeSats. And then in 2012, these standards were fixed. So we were able to launch even more. So as you can see, from 2012 and going on, now you can see the exponential growth. Now we exceeded the 1,000 CubeSat mark, and we're still going. On the right, we can see the mission, the CubeSat mission types. So if you can see, it started as university missions, university CubeSat mission types, and they are still growing. And if you can see, it's mainly dominated by universities still, even though the commercial or private companies are interested in CubeSats, but still universities are really stressing on CubeSat, are really working on CubeSat, since they provide a very, very, very important benefits for educational or the academic field. Let's focus on the university class spacecraft, since this is my focus in the presentation. We can divide the university class spacecrafts into three. A flagship university, where they launch a spacecraft every few years. They have a history in space. You have other prolific independent universities develop their own successful missions, and the hobbyists who are trying to reach or to build their successful mission. Now moving on, let's look at their mission status. So what are the outcomes from all these university class missions? If we look at the figure on the left, all university class missions, we can see that if 12% is launch fail, 25.7% is dead on arrival, and 13.3% early loss. So it's around 50% of the missions have failed to reach their primary objective, which is very bad. So let's split it out and look at each university type on its own. Starting with regular universities, they have actually 65%. If you look at 44%, including the early loss, it's actually 65% loss of mission. Then moving on to the independent universities, you can see it's a little bit better. And then flagship universities, they're better and better, around 25% failure rate. It's still high, but it shows that as universities keep on keep on working on space missions, they're improving drastically. So the question I believe that you should ask right now after seeing all these failures, you can say, so is it worth it to invest in these missions? Since we're getting so many, like, if we're talking 65% failure rate for new universities and 25, it's pretty high. Now, to answer this question, we have to look at two main things. First of all, the scientific outcome and the educational outcome. So the scientific outcome was covered in Ibrahim's part, where he talked about Sharjah-Sat's scientific objective and what we will get from this, which is pretty impressive from the X-ray detector. And then the second part, which I'll cover here, is the educational outcome. So what will you get as a student or as an engineer in these CubeSat missions? Starting with the technical outcomes, you will develop a good or deep skills in the subsystem that you're working on, okay? And after that, and also you'll have an overall space mission design knowledge. So for every space mission, we start by having the requirements and constraints. After that, you keep on doing the iterative design process and the trade-off. So if, for example, the weight, you have a limited budget, you look, okay, should I choose this or that? For the power, am I supplying enough power? For the size, the physical size, can it be folded or not? For the attitude control, can I use passive, just use the magnetic field to orient my spacecraft? And all these decisions that can be taken that will develop all these technical skills as an engineer to choose, to make the decision. Another outcome, which is very important, is that any spacecraft mission is actually an interdisciplinary field. So either if you're talking about the EPS, electric power system, ADCS, command data handling, communication, thermal structure, or propulsion. So during the mission development time, you will meet the, if you're using a propulsion system, you'll meet the chemical engineer, you'll meet the thermal engineer, the structural engineer, the software engineer, the communication engineer, the electrical engineer, the mechanical, and the aerospace. So all of them are working together. So in this way, even if I'm working as an aerospace engineering student, I can understand what's happening in the other subsystems because I'm limited with their requirements. So if I take a decision, it's actually limited by, for example, who's the power engineer, who's managing the power budget. He'll tell me I can't exceed this due to the efficiency of my solar panels. Another outcome that is very important is the professional outcome. So students and young engineers require this transition to join the space industry, which takes a lot of time if you're jumping from university straight ahead to big projects or to the field. So it should take time, and CubeSat missions or university class missions are very, very helpful to ease that transition. Now, of course, these missions can be added to the framework to the academic framework, allowing them to gain hands-on experience before graduating, especially that these missions take less time. Also, these missions are highly motivational. Imagine working or designing something and it flies to space, which is very inspirational. Also, students will be able to identify areas for improvement. As I said before, when you're working with electrical engineers, chemical engineers, and this, you'll understand where are your weak points and what are you strong on. So you'll know what to work on. Also, so here at our CubeSat workshop and courses, what we have done throughout this time, starting with the CanSat workshop, where 79 students participated in this CanSat workshop, working on 15 different CanSat projects. Also the Arduino workshop, which shows them the concept and the methodology of Arduinos and how we can use them in different projects. Also the AGI STK workshop, which is a software package used by engineers and scientists to do this complex analysis for these missions. Another thing is the 6-week CubeSat course, where students were able to have a hands-on and build a simplified CubeSat while in this course. Another very important thing is the summer internship students. We had them last summer, and we are constantly having them. Last summer, for example, they worked, or this summer, they worked on 3D experience, STK, and different modules to design the whole thing. And currently we have a nuclear engineer student doing the summer internship, which is pretty interesting because she's trying to review the possibility of replacing the power system with a nuclear source. So we should see what we'll get at the end. So in conclusion, CubeSat missions provide valuable training and experience for young engineers. Even with the high failure rate, it is shown that as soon as, or when universities keep on working on these missions, the success rate increases significantly. And as long as the satellites are placed into a naturally decaying orbit, a low risk for space junk. And that's all from my side. Thank you. And if you have any questions, please go ahead.
Thank you very much, Mohammed, for this very educative lecture about the use of CubeSat and how important they are in terms of the education, in terms of getting the right student to the right knowledge, because as we said, the CubeSat has so many different components, and for each component you have a specific engineer. So this since more than 2.5 years, or more, maybe 3 years, with all what you have mentioned in your last slide, this STK workshops, this CubeSat course, the Arduino workshop, the CANSAT, I believe, were able to teach and to online to give light to hundreds of students that did visit the Sharjah Academy for Astronomy, Space and Technology. I believe every one of them, we remember for a long time that experience that he had building a CANSAT. We built about, I believe, more than 10 CANSAT, and we went out here outside the building to check them out, and it was a wonderful experience. I believe some of the videos are on our website. So thank you again. Thank you, Mohammed. Thank you, Tarifa. Thank you, Ibrahim. So let me open the floor. So please, if you have a comment, a question to the group, so please feel free. Any questions, any comment, please? Well, let me add one comment. You talked, Mohammed, about the failure of this small satellite. So more than 50% of them, so they never reach orbit. And even if they do reach orbit, some of them will get into trouble. That's why it is a very tricky business to send even a small satellite. So you need to have that know-how. That's why it's good when you have that capability to teach other groups, other universities how to do it. That's why we are in collaboration with Istanbul Technical University to avoid all of such a problem. That's why as we learn also their mistakes, what they did wrong during the past missions. But everything has a start. For us, we say it is normal. But the main thing that you get that space education, how to bring all of the elements, how to all of them to communicate with each other, the least problem. This is what is all about building a CubeSat. Okay, it is not just putting elements together, it's to know exactly how each of the components is going to affect the other one. Since you are quite power limited, so you must be very efficient. in doing so. But even as we said, even if it is a failure, so the main thing that students did learn something. And if they go into space application, into space engineering, so they have that background and they have it on their CV, and that's very important. Any other comment, please?
Yes, I would just want to add that exactly what you said. Collaboration is the key. So if we have flagship universities and we have top universities or universities that have successful missions, if they collaborate with regular universities or universities that are just starting, you overcome all these challenges, because most of these field missions, they are actually universities who try to do it on their own. And then as soon as they fail, they stop trying. So this is the problem. So collaboration is a really good key.
Yeah, that's very important. Yesterday we had a meeting with Scotech University, and they have a space center there, and they are very well versed in CubeSat and also bigger satellites. That's why it would be good to have some kind of collaboration with them in the future. We may also expand that collaboration to other countries, not only with the Russian. So we have it now with Istanbul, so we can have it with France and so on. And yesterday we had this meteorite talk by Miriam, and she mentioned several good CubeSat dedicated to meteors, to meteorite. These programs are very important. So that's why I said yesterday, the CubeSat Lab and the Meteorite Center have to meet and to talk about this program. So is it possible to at least imitate one of them and see, because these programs, from what I know, they were not launched until now. So we may contact the principal investigator of this CubeSat, and we may have some kind of collaboration in the near future. How to use them in terms of meteors observation. It is not only for meteor observation. It may be also, as Miriam mentioned, also to detect natural artificial space debris. So we have them all around us. So it would be good to see. I know that the Japanese are doing it because they visited us about 2 years ago in 2018. So we had a workshop on that, and they have several programs. I don't know if they were all launched or not yet. So we have to follow up on that. Great. Okay, any other question, any chat, any comment, any advice, please? Just one note. We're supposed to have our activity tomorrow for the World Space Week between 12 o'clock and 3 p.m. But tomorrow there's university big meeting in terms of the strategic plan. That's why I talked to the high energy physics group, and we are shifting it to Friday. Friday it was supposed to be the radio astronomy group. It was shifted to Saturday. So now tomorrow there will be no World Space Week activity. There will be on Friday and on Saturday around the same time. And if there is any change of time, we're going to let everyone knows about it. Okay. Okay, so thank you very much, all of you. Thank you very much. We appreciate all of your participation, and see you then on Friday.
Thank you.
شكرا. السلام عليكم.